Hello, and welcome to the next video in my series on operations management. Now, just a reminder that these videos are geared towards people that are new to operations management. So if you are working on your MBA somewhere, these videos are probably a bit below what you would need. However, if you just want the basic ideas in operations management, then these videos are for you. Now, I will say for this video, you will need some basic understanding of algebra to really get to the core of our topic today. So let's go ahead and dive right in. In this video, we will be extending our discussion on time series forecasting. In my previous video, we talked about simple moving averages and weighted moving averages, and in this video, we're going to talk about the exponential moving average, which is actually a specific type of weighted moving average. So in this video, we still have the same problem, and that is where you're working in the Office of Institutional Research for a large Midwestern university here in the U.S. The administration has tasked your office with producing enrollment forecasts for next year based on historical enrollment data. Now the questions are, how can we make this forecast using the exponential moving average method? And how does this method compare to the simple moving average and the weighted moving average? Now, we have discussed three possibilities in other videos, so the exponential moving average will be our fourth. Now, just to review, the first approach is the naive approach, and that's just where we use last year's data point to forecast this year's. We just use the same information. And then, of course, we had the simple moving average, where we take a certain number of years in the past, average those together, and then that's our new forecast. In our previous video, we selected 3. So we averaged the 3 previous years from now, or in the past from now, added those together, divided by 3, and that was our new forecast. Then we had the weighted moving average, which is similar to the simple moving average, but for those 3 years in the past, we gave each year a weight. So last year was weighted a lot more than the year before that, and that year was weighted a lot more than the year before that. So we gave more emphasis to recent year's data. Now, of course, this video is about the fourth option, which is the exponential moving average. And this is a specific type of weighted moving average. And I give this the phrase constant calculations because the EMA involves using a smoothing constant, and we'll talk about what that is here in a couple of minutes. So just a reminder, here is our enrollment data, and this is the enrollment data for IUPUI in Indianapolis, Indiana. And I've just been researching that university recently, so that's why I use this data. I just had it available. So you can see the enrollment from 2002 up through 2011 has gone up from 29,025 up to 30,530. So again, of about 1,500 students over that period of time. And of course, we are tasked in this problem with figuring out what the enrollment or the forecast will be for 2012. So here is a graph of the enrollment from 2002 to 2011. As you can see, we had a low year in 2002. The enrollment shot up quite a bit in 2003, flattened out. Then we had a little bit of dip in 06 and 07. And then it rose again from 2008 up through 2010, and 2011 was pretty much the same. So what exactly is this exponential moving average? Well, as I mentioned, it's a specific type of weighted moving average. It requires very little historical data to implement, which may be good depending on your situation. It's very flexible with regard to weighting past data. So we could choose, just by changing one number, whether we want to emphasize more recent data or we want to include data from many years in the past. It's just as simple as changing one number. So here's the basic formula for the EMA. Now, to find our new forecast, we're going to do the following. And I'm going to start on the right-hand side of this equation because I think it's easier to start there. In the parentheses, we're going to take last period's, and in our case, last year's actual enrollment. And then we're going to subtract last year's forecast. So last year's enrollment minus last year's forecasted enrollment. Then we're going to multiply that by alpha, which is our smoothing constant, and we'll talk about that here in a minute. Then we're going to take that and add it to last year's forecast. So as you can see, the math involved is fairly simple. We just need a couple of bits of information and the constant we choose. So to conduct the EMA, we only need 3 pieces of data. We need last period's forecast, and in our case, that's last year's forecast. We need the last period's actual value, so in our case, that's last year's actual enrollment. And then we need alpha, which is the smoothing constant, and we get to choose that. So as you can see, there is not a whole lot of information that's needed to use the EMA. We just have to make sure we have last year's forecast and last year's actual data, and then the alpha we choose. Now one note, when we are starting a time series at time 0 or year 0, well, we don't necessarily have last year's forecast. So in that case, we assume that for our next forecast, the forecasted and actual value are treated as the same. Now that may be a bit confusing right now, but when we do the example, you'll see exactly how that works. So what exactly is this smoothing constant alpha we've been talking about? Well, alpha is a value between 0 and 1. And it's never going to be 0 and it's never going to be 1 for reasons I will explain here in a second. Now, most applications are going to call for a value in there between 0.05 and 0.50 because strange things begin to happen when the values are more or less than that, and we'll talk about that here in a minute. Now, the EMA incorporates previous periods' forecasts, unlike the simple moving average and weighted moving average. If you remember, in those two, we were only using prior years or prior periods data. In the simple moving average, we just picked a certain number of years we wanted to average together. We averaged those years together, and that was our next forecast. In the weighted moving average, we picked a certain number of years we wanted to average together, but for each individual year, we gave each one a weight, and then we divided by the sum of our weights. In neither case did we use any forecasted values. We were only using actual historical data. But in the EMA, we are actually incorporating the prior year's forecasts, and that's what makes it unique. Now, the closer to 1 our alpha value gets, the more the exponential smoothing constant emphasizes recent actual values. So in our case, the closer to 1 of an alpha we would choose, the more it's going to emphasize the recent actual value. Now, the extreme case is that the closer to 1 it gets, the more it resembles the naive method, because if you remember, in the naive method of forecasting, we just use last year's actual data. So if our enrollment was 30,000 last year, in the naive method, our forecast is going to be 30,000, because we're just using that last year's data point. So in the EMA, the closer to 1 alpha gets, the more it resembles that. Now, at alpha of 1, the EMA is the naive method. So at that extreme value of 1, the EMA and the naive method of forecasting are the same. So again, that's why we would not choose an alpha of 1, because basically that is the exact same as the naive method, and we would just choose last year's data point or last year's enrollment, and that would be our forecast. Now at the other extreme of alpha equals 0, the EMA is, well, it's kind of goofy because our new forecast would be the same as last year's forecast. Now think about that. Why would we do that? That doesn't incorporate the actual data point from last year. So you can see that at these extremes, 1 and 0, the EMA doesn't really do us a whole lot of good. At 1, it's the same thing as the naive method, which is last year's enrollment. We just use that. At alpha equals 0, the EMA is last year's forecast, and we would just use that. So we're looking for some middle ground between those two, and that's really all the alpha constant is. It's incorporating a proportion of last year's forecast and last year's actual data to come up with our new forecast. So just think about what the extremes represent and realize that when we choose a value between 0 and 1, it's kind of a sliding scale. If we go towards 1, we're going to be emphasizing, very recent data. If we go towards 0, we're going to be emphasizing more data into the past. Now, if there's one slide in this presentation to really sit and look at, if you really want to understand what's going on in the exponential moving average, this is it. So I urge you to pause it, really take a look at this slide, and if you really understand what's going on, then you really are getting the core concept of the EMA. Now over on the right hand side, I've selected different alpha values. So 0.5, 0.4, 0.3, 0.2, and 0.1. And of course those correspond to curves on our graph. And let's look at alpha of 0.5, which is the red line on our graph. Now if you notice, we have a curve that starts at the top left, goes down fairly sharply, and then bows and then flattens out towards the end. Now each point represents a number of periods or number of years in our case in the past. So we have last period right on the axis, then we have 2 years ago, 3 years ago, 4 years ago, 5, and 6. On the y-axis up and down we have weights, and that is the weight we're going to give that year. With the alpha of 0.5, we're going to give last year a weighting of 0.5. Then we're going to give 2 years in the past a weighting of 0.25. And then 3 years in the past, we're going to give that a weighting of 0.125. And you can see in this case, we're just having that value each time. So this creates what's basically an exponential decay curve from the top left down to the right, where each year is weighted less and less and less as we go on. Now as you can see, as we get down to 6 years in the past, the weighting for the alpha of 0.5 is getting very, very close to 0. Now the thing is, because this sort of represents it does represent a fundamental function in mathematics, it will never actually reach 0. It's what we call an asymptote. However, for our use, just remember that that red line is going to curve down and flatten out, but it's never, ever, ever going to really reach 0. Now let's look at the alpha of 0.4, which is the green. Now if you notice, that curve is a bit shallower. So it starts at a lower point and it's flatter as it curves down and to the right and actually finishes above the alpha of 0.5. Well, think about this. What does this mean? Well, if you look at the last period's weighting, instead of 0.5, it's now 0.4. Now if we go down to 2 years ago, instead of the weighting being 0.25, which it is at the alpha of 0.5, it's going to be below that. As we go down to 3 years ago, well, look at that. Our alpha of 0.4 is actually above our alpha of 0.5. And that's because the decrease in weighting over the years is less severe. And that's why the green line, the green curve, is flatter. And over time, it will go further out to the right than our alpha of 0.5. Now look at the same thing for alpha of 0.3. Our weightings start at 0.3, and that purple curve is much flatter. So last period's weighting relative to 2 years ago, the difference between them is much less severe than it is for the alpha of 0.5. And all this means is that we are giving more emphasis to data in the past. So with the alpha of 0.5, we have a lot of emphasis on last year, some emphasis on 2 years ago, a little bit of emphasis on 3 years ago, and then it really goes down really fast. Now if we look at the alpha of 0.3 or even 0.2, we're not putting nearly as much emphasis on last period relative to the 0.5 alpha, but as we go back through time, the weightings are much more even. So from year to year, the weightings are relatively more emphasized, I guess you would say. And of course, the extreme example is the alpha of 0.1. So look at that. That's the orange line. It's basically a flat line that goes slightly down and to the right. And what does that tell us? Well, that tells us that last year, 2 years ago, 3 years ago, 4 years ago, 5 years ago, 6, 7, 8, 9, 10, 11, actually all the way out to 19 years ago, are going to have relatively close weightings. Whereas like in 0.5, all the emphasis is up front last year and 2 years ago. So here you can see that by choosing different alpha levels, we can shift the emphasis on more current data versus data in the past. With a higher alpha like 0.5, we're going to emphasize the past couple, 2, 3 years the most, and then beyond that, those years aren't going to have a whole lot of impact. However, with an alpha, say, of 0.2, last year, 2 years ago, and 3 years ago, and 4 years ago, those are going to contribute relatively equally, but at a decreasing rate, to our forecast. So, like I said, that's a very long explanation of this slide, but if you really want to understand what's going on, what the alpha value is actually doing to our data, this slide is it. All right, so let's go ahead and look at our enrollment data, and we're going to choose an alpha of 0.5. So this corresponds to the weighting graph that was the red line in our previous slide. So it's going to emphasize last year, it's going to emphasize the year before that, half of that, the year before that, half of that, and so forth. So the weighting is the red curve in our previous slide. So let's go down to the very bottom, and you'll notice that the two cells in the lower right are blacked out. And that's because, remember that in order to calculate the EMA, we have to have information about the previous year, but in the 2002 case, we do not. So we cannot really calculate that information for 2002. However, we can for 2003. But the only information we have for 2002 is the actual enrollment. So if you remember, I said in my little note in a couple slides ago that in our first case, since we only have the actual enrollment data for 2002, that will actually be our actual and forecasted data when we're figuring out 2003. So if you look in the formula column, over on the right-hand side in the parentheses, we have 29025 minus 29025, and that's because that's the enrollment in 2002. We multiply that, of course it's 0, by 0.5, which is still 0, and then we add that to last year's actual enrollment, which was 29025, so our forecast is 29025. Again, that's kind of the drawback of starting this time series like that, but that's what we have to do in this example. It really gets interesting in 2004 because now we have some actual working data to go off of. So if you look in the parentheses of 2004, you will see that we have 29860. Well, what is that from? Remember, that's our enrollment, our actual enrollment from 2003. So that's 29860 minus our forecast from 2003. And that is 29025. So 29860 minus 29025, that's our actual and forecast from 2003. We multiply that by 0.5, and then we add it to last year's forecast, which was 29025. And that gives us a forecasted enrollment for 2004 of 29,443. All right, let's do one more, and then you'll see the pattern. So for 2005, if we look in the parentheses, we have 29953. And of course, that comes from the actual enrollment for 2004 minus the forecast for 2004, which is 29443. So we subtract those, multiply by 0.5, and then we add that to the forecasted value for 2004, which was 29,443, and we come up with a forecasted enrollment of 29,698 for 2005. And then the pattern just repeats over and over again as we go up our chart. It's just that simple. We just insert the prior year's actual enrollment and forecasted enrollment into our formula, calculate it, then we go to the next one. Do that and go to the next one. That's it. So if you want, go ahead and take a look at this slide for a minute, but I'm going to go ahead and continue. So here is the graph of our actual enrollment versus our forecasted enrollment using the EMA with an alpha of 0.5. Now, I do want to warn you about this graph. The first data point is going to be deceiving. Because remember, we didn't have any other data to go off of except for that first year's enrollment. And especially in this case, that first year's enrollment was quite low relative to the other data points. So it's really going to drag down that first EMA of alpha 0.5 in the blue there. So you really want to pay attention to the EMA at around 2005, because then we have a couple of years to work with. Now, if you notice, it follows along our actual enrollment, and then in 2007 it kind of diverges a bit before catching up, over the course of the next 3 or 4 years. And that's just a common trait of all moving averages, is that they tend to lag behind the actual enrollment. So in the enrollment, our dip is in 2006, 2007, but in our EMA forecast, our dip is in 2007, 2008, and then it catches back up again. So there is some lag, just like other moving averages, in the exponential. Now look at this. Now remember when I said that extreme alpha values start behaving very strangely. Now here, we have the same graph we did before, but then I reran the numbers with an alpha of 0.1. Now, let's review. If we have a very low alpha, what are we getting close to representing? Well, with a very low alpha near 0, we're actually getting close to forecasting our next year based on this year's forecast. So an alpha of 0 would just be repeating this year's forecast over and over again. So if we look at our alpha of 0.1, it's very, very low. It's extremely far below the actual enrollment in the alpha of 0.5. Because all we're doing is basically using our forecast over and over again with just slight modifications or slight input from the actual enrollment. That's what I mean by extreme alpha values doing very weird things. So let's go ahead and look at another extreme value just so you can see how it works on the other side. Now in the green, I've picked a very high alpha of 0.75. By all evaluations, that's even worse. That's even below the alpha of 0.1. So what's going on here? Now remember what I said is as the alpha gets close to 1, our forecast is the previous year's actual enrollment, sort of the naive method. So when we start out in 2003 with that low enrollment around 29,000, well, we just keep using that figure over and over again with slight modification by the actual enrollment. So the thing I want to point out here is in the yellow line, we keep using last year's forecast over and over again. In the green line, we keep using last year's actual enrollment over and over again, each with slight modification by the actual enrollment itself. Now with the alpha of 0.5, we have sort of that middle ground, where we're using a better proportion of last year's actual enrollment and last year's forecast. And of course, that's much more realistic and valuable to us. So I just want to show you the effects graphically of choosing extreme values at the low end and at the high end of our 0 to 1 alpha range. So just like every moving average, the EMA has some pros and cons. Of course, just like other moving averages, it can smooth out random blips in the data. The EMA is flexible since we can choose our alpha. Now we could run our EMA with different alphas and then measure how close it gets to our actual enrollment. And actually, that's going to be the next series of videos, so watch out for those. But we could easily change the alpha around to see which one works best. We only need the last period's forecasted and actual value. That's all we need to run the EMA. Now for some cons. The best value for alpha is in a very narrow sort of sweet spot. Unless you know a lot about EMA and have done it many times over and over again, or you know the characteristics of your data, it can be hard to determine where that sweet spot is. You just kind of get a feel for it as you do it. And of course, the best way is always to graph it and look at it. Now, like I said, we're going to be using some error detection techniques in our next video, so you can figure out which alpha and which method works best. But it can be hard to find that perfect alpha value for your data. Now, extreme alphas, as far as the exponential smoothing constant, can turn last period's value into your data point, or it can turn last period's forecast into your data point. So again, you got to watch out for the extreme values of alpha, or you're just repeating last year's data or last year's forecast. Now, like other moving averages, the exponential smoothing, or the EMA, lags behind the actual values because, again, it is using prior year's data and prior year's forecasts. Now, the exponential smoothing is partially dependent on last period's forecast. So that's kind of at the core, again, of what the EMA is doing, is that the forecasts over prior years are continually built in to the next year's forecast. Okay, and I don't want to get into the mathematics behind that, but instead of using actual prior year's data, we are incorporating the actual prior year's forecasts into it. So if those forecasts are way off, they're going to be sort of churned in to our current forecast. And of course, in our case, we saw how that worked, but it can create an awkward beginning point. So the first data point in our series is much lower than the rest. So we needed a few years for our EMA to actually catch up to the actual data because of that odd first year. So remember, we were tasked with finding the enrollment for fall 2012 using EMA. So remember, in the naive approach from our last video, in 2011 our enrollment was 30,530. So if we do use the naive approach, we're just going to assume it's the same. So our forecasted enrollment for 2012 would be 30,530. Now, using our simple moving average, we just added the prior 3 years enrollment divided by 3, and that gave us a forecasted enrollment of 30,493. Now, using the weighted moving average, we took the last 3 years, but we weighted each one differently. We gave last year a weighting of 4, the year before that a weighting of 2, and the year before that a weighting of 1. So we weighted each value divided by our total weights, which were 7, and we came up with a forecasted enrollment of 30,519. Now, how about our EMA method? What do we come up with for this? So using an alpha of 0.5, we came out with an estimated or forecasted enrollment of 30,462. And again, that's based off 2011's actual enrollment and 2011's forecasted enrollment. So if we look at these, we can see that our EMA is actually the more conservative of the 4 methods at 30,462. And then the simple moving average was 30,493. And then they go up from there. But still, these are all well within 100 students of each other. So actually even less than that. So we have a low of 30,462 and a high value of 30,530. So we're well within 100 student difference within all 4 methods. So you can see the method you choose really just depends on the nature of your data. Okay? And luckily they're all simple enough where you could actually test each one out to figure out which provides the closest measure to the actual data you have. So we practiced on the 2003 to 2011 data to kind of figure out which method worked best with the trend and history of our data. So when we make our fall 2012 forecast, we'll know which one in general works best. Now, we haven't figured out the error for each method. That's going to be in our next series of videos. But, for our purposes, really, any one of these would work because they're all so close. If one was really off, then we would probably want to look at that one or even discount it. Now, if we graph all of this on one graph, it's really easy to see. So our enrollment is the orange line in our graph, the orange curve line. Our 3-year simple moving average is in yellow. Our 3-year weighted moving average is in blue. And our EMA with an alpha of 0.5 is in the red. Based on this graph, which method would you choose? Well, based on this graph, I would choose the 3-year weighted moving average. And why is that? Well, it follows our actual enrollment a lot closer than the other two. It's pretty close. The blue line is pretty close to the brownish line all the way through. I mean, that's actually, pretty good. And actually, they end on almost the exact same point. So, in this case, I might stick with the 3-year weighted moving average. Now, for a different data set, another one might be better. It just depends. So again, that was just a little introduction to our exponential moving average. Thank you very much for watching, and I look forward to seeing you again next time.